Okay, so in the final part of this lecture, we are going to describe a second estimation technique. This is what's often called a discounting method. And this will build on many of the same intuitions as linear interpolation, but as we'll see, it's a slightly different way of doing things. And it's also very often used in practice. Okay, so to understand discounting methods, let's first start with an intuition illustrated by the example I've shown here. So what I've shown is the counts for bigrams where the first word in the bigram is the word there. So for example, there followed by dog is seen 15 times, there followed by woman is seen 11 times, and so on and so on. And I'll assume in this example that in this list I've shown all bigrams whose count is greater than 0. So I have the full list of words which are seen one or more times following the word there. There are about 10 of these words in total. And so the number of times I've seen the word there is going to be the sum of these counts. It's actually 48 in this case. So now if we consider the maximum likelihood estimates in this case, they're going to be, for example, 15 divided by 48 for the probability of dog following there, 11 out of 48 probability of woman following there, and so on, just the ratio of this count to the total number of times that I've seen the word there. Now, one thing to observe here is that, in general, these estimates are going to be systematically high, particularly in cases where we have a large vocabulary. Remember, we might have a few thousand or tens of thousands of possible words following the word there, but we've only seen the word there 48 times, and so it's just a lucky few words which are actually seen after the word there. And that's a rather informal description, but you can actually show rather more formally that these estimates are going to be systematically high. That's particularly true for these low count estimates. For example, the probability of street following there being 1 over 48 is going to be a rather high estimate in this case. So discounting methods build on that intuition in the following way. We're going to define these new discounted counts. I'll use count star to refer to a discounted count, as simply count of x minus 0.5 for any bigram x whose count is 1 or more. So looking back at this example, if the count here is 15, for example, the discounted count is going to be 14.5. Similarly, an original count of 11 translates to a discounted count of 10.5. And for all of these cases where the count is 1, the discounted count is 0.5. And we can again define estimates now based on the ratio of the discounted count to the number of times we've seen the word there. So for example, we now have 14.5 out of 48 as the estimate for the probability of dog given there, or 0.5 out of 48 for the probability of country given there. So notice we've essentially lowered each of these estimates through these discounting methods. Now, once we've done this, we'll see that there is actually some missing or left over probability mass. What do I mean by that? Well, if we sum each of these terms, we end up with an expression, something like 14.5 out of 48 plus 10.5 out of 48, and so on and so on. Finally, we have plus 5 times 0.5 out of 48. That's actually a value which is 43 out of 48, if you do the calculation. And this is actually less than 1. Okay, so we have a series of probabilities which sum to less than 1. And that leaves some so-called missing probability mass, whose value is 1 minus 43 over 48, this is equal to 5 over 48. This is, in a sense, the probability mass that we have left over after this discounting method. Now, the basic idea in discounting methods is going to be to take this missing probability mass and divide it between other words in the vocabulary which aren't in this list, i.e. words where the count following the word there is equal to 0. Those unlucky words which were never seen in a bigram with there as the first word. So a little bit more formally, we'll define for any word wi minus 1, alpha of wi minus 1 to be this missing probability mass. And this is defined as 1 minus, here I have a sum over w, count star of wi minus 1w divided by count of wi minus 1. So in the particular example I just showed you, you can verify that this missing probability mass is in fact 5 out of 48. So let's see how we can derive the final estimate based on this discounting method, following this idea of dividing the missing mass between the words whose count is 0 for a particular contextual word. And this is a method going back to Katz, so it's often called a Katz back-off model. And here we're deriving a bigram estimator because Q of BO, this is going to be the backed-off estimate of WI versus conditioned on WI minus 1 is going to condition just on the previous word. In a moment, we'll see how to define a trigram estimator in a similar way, but first of all, we'll consider the bigram case. Okay, so for a particular word, wi minus 1, I'll define two sets. So big A of wi minus 1 is the set of words whose bigram count is greater than 0. So for example, for the word there, it would be the 10 words that I'd shown you on the previous slide. In contrast, B of wi minus 1 is the set of words for which the count is equal to 0. So this is the set of words which are never seen following the particular word we're interested in. As before, I'm going to define the missing probability mass through this expression. This is going to be 1 minus. Here I have a sum over all the words whose count is greater than 0, count star of wi minus 1w divided by count w minus 1. So this is the probability mass which is left over. Okay, so given these definitions, the backed-off estimate takes two forms depending on whether a word is in the set A or if a word is in the set B. If we have a word in the set A, we simply take the discounted count, so this might, for example, be 0.5, divided by the number of times we've seen wi minus 1. So this might be 48, for example. Conversely, if the word is in the second set B, that means this count is equal to 0, we do the following. So remember that alpha of wi minus 1 is this missing probability mass. I said before we were somehow going to divide this between the different words in this set B. And we divide this in proportion to the maximum likelihood estimate at the unigram level. So QML of WI is the unigram maximum likelihood estimate I showed you earlier. So in the numerator, that's what I have here. In the denominator, I have a sum over all words in B and QML of that W. And so this is just a normalization term which ensures that I'm splitting the alphas in proportion to these unigram maximum likelihood estimates. So you can see once we've defined these discounted counts through, for example, subtracting a value like 0.5 from each count seen in training data, it's really quite simple to derive this, this estimation method. And it works really quite well in practice.